Hello and welcome. I hope you are having a great day. In this video, we are going to discuss about understanding data distribution from statistical point of view. Okay, so let's begin. So let me set up the agenda first. I hope the screen is visible. This is the topic. So this will be a statistical point of view. From statistical point of view, this will be the fundamental class for statistics. Okay, the beginning. So till now, when we are discussing about probability, we discussed about PDFs, PMFs, where we understood the distribution of the data from probability perspective. Now we will understand the same distribution from statistical perspective, because always we may not have the PDF or PMF, so these functions may not be available for the data. So what do we do? So we'll just get the data points, data sets, x1, x2, x3, like this. So in this case, first of all, we start with the statistical analysis of the data, and that's what we do whenever we in machine learning also. So the first thing we do, exploratory data analysis, EDA. Okay, exploratory data analysis. So these concepts will be used in doing that, for understanding what is my data about, what is it, what is the mean, what is the median, etc. So this video is about that. Let's begin. So the agenda of this video would be, the first thing is measure of central tendencies of the data, that is mean, median, mode. Then we'll discuss about measure of dispersion, that is these are measured by range, variance, standard deviation, mean absolute deviation, also called MAD. Then skewness and kurtosis. We have discussed about variance, skewness and kurtosis earlier also when we were discussing moments. So these are the various moments of a function, of a distribution. So this is second moment, this is third moment, this is fourth moment. Okay, so these are most prominent moments. So this tell me what is the spread of the data, how the data is placed, how whether it is close to the mean or it is spread out, how skewed the data is, how fat or thick the tail is, if it is a tail data distribution. Okay, so these will be measures of dispersion. Then we will move on and discuss measures of position. Position would be the relative position within the data. So if you have n data sets, data points within a data set, so what is the relative positioning of the data points within the data? So that will measure using percentiles. You must have heard percentiles. We'll formalize that understanding. Quantiles, and one more concept, that is interquartile range. Okay, that is used for outliers. This is the most common concept used for identifying outliers. Okay, simplest when we are doing the EDA. So these concepts will be serving as foundation for the EDA and the basis of statistics when we just have the data and how to understand the data that we have. Let's begin. So first topic, measure of central tendencies. So what is the central tendency? What do we mean when I say measure of central tendency? So let me write it down. Measure of central tendency of a data. Measure of central tendency. Central tendency means a single statistical value that describes the typical, when you from a sample, if you take any point, okay, so it should tell me that this is the typical data about. Okay, this is the typical. Say for example, if I take any person from India and take a typical person out, what would be his height, a male's height? So we'll say that that's like 5.5 feet. So that's a typical Indian. So that's the average height of an Indian. That's what we talk about. So that's the measure of central tendency. That even if I take a typical data point, that should be representative of the data, and that would be good enough, and that will be acceptable. That's what I mean when I say measure of central tendency. That this should be a representative or a typical data point. So most of the people would be around this, or most of the data points would be around this, and that will be a representative. Okay, when we talk about mean. Okay, and others also. Okay, others also. Sorry, mean, median, and mode also. We'll see in what context what, but this can be taken as the representative of the complete data set. That's what measure of central tendency means. Okay, let me write it down. So measure of central, this is so out of the multiple data points, a single statistical data point will give me one value that is representative. A single statistical value that describes a typical or central point, a representative, a typical or central point of data set. Okay, so this is a representative, as I mentioned, this is a representative, single representative. And most of these concepts you must have learned in school itself. Okay, this is just a revision and plus more information around how we understand it with respect to data and machine learning. Okay, some more insights based on the fundamentals. So this is what it means. Why did we learn these concepts? Because when we have a data point, and this can be used for comparing central tendencies. Means, say for example, this is for a single data set. For example, I have two sets of people. Okay, so I have people from okay, one class, okay, and people from another class. Say standard, you have like people from one standard 5 class and then standard 8 class, and you measure all the people height and take the average height. So you can compare two group of children height now, right? So standard 5 children will be smaller on an average than standard 8 children. So that's what we can compare to. Are all children taller or smaller in class 5 or than the children in standard 8? No, right? So we take one representative, which will be the average, and we can compare two groups using this central tendency. That this is a typical or representative data which represents these two groups, and now I can compare these two groups using this central data point or the typical data point on the representative data point. And that's what this measure of central tendency means. I hope this measure of central tendency is clear now. Why are we studying these things? Always I'll go via this flow only. Why are we studying this? Okay, so the first thing would be mean. We have studied this a lot. When mean means mean or average. We know this. Okay, this is the most common. This is the most common we use. This is most common. Okay. Now what is mean? It is simply but okay. Generally we say this is the balancing point of the data set. Mean would be like just at the center. It's balancing point of the data set. Okay. And for example, if I say there are 5 data points. Okay. Mean of, I'll take very simple example so that just the intuition is clear and then I won't complicate the maths. So this would be sum of all 1 plus 2 plus 3 plus 4 plus 5 by 5, and this will come out to be 3. Okay, so you know this is the average. Sum of all by the count. This is n and this is sum. This we know already. Okay, and if we go further, so there are two kinds of means. One is sample mean. So we have a sample which we take as a representative of the population generally, and one we have population mean. That is for the complete population. For example, we say that average height of Indian people is 5 feet 6 inch. So that's the population mean. This is mu. Okay, represented by mu. But are we going and measuring the height of each and every person in India? That's not the case, right? So what do? We take a sample, and that's what is assumed to be a good representative sample, and this data, whatever it comes out, that's a good representative of the population mean. So this is your population mean, this is your sample mean. Okay, and then we'll further read about central limit theorem, etc., which will justify how this sample mean can be taken for all practical purposes when n is very large. That is the equal to population mean. Okay, but this is for understanding. X bar is sample mean and population mean is mu. Okay, that's the simple. So what are the good things about it? What are the pros? So I'll make comparative analysis. So what are the pros of this? So pros is that we are taking all the data points. So all these data points are taken into consideration because we are summing up all the data points and then we are taking the average. So all the data points are included. Okay, that's the pro. All data points are considered. Okay, and what is the cons for this? That if I have an outlier, it is highly sensitive to outlier. Highly sensitive to outliers or extreme values. in my data set, outliers or extreme values. Outliers means extreme values. For example, if I have, for example, my same data set is, if I have to find a mean of 1, 2, 3, 4 and 100. So instead of 5, now I am having 100. So this is an outlier, extreme value. All these were in the same range, but this is an outlier, extreme. But what will be my mean? What will be my mean now? This will be 1 plus 2 plus 3 plus 4 plus 100 by 5. This will become 22. So see, my earlier mean was 3 and just one outlier brought it to 22. So this is very sensitive to outliers, my mean. So that's why we have to handle these mean outliers or some other mechanism we use. Okay, so you can see that in this data there's nothing like 22. Most of the data is 1, 2, 3, 4 only, but just 100 is pulling it to 22, and we are telling that okay, this is the representative of the complete sample, but that's not the case. This is happening because of the outlier we have. Similarly, if the outliers go even high, 1000, it will just pull the value towards it, which will not be the representative of the data. So this is a con of this measure. So that's why we have different kinds of measures. Just mean would be sufficient otherwise. So to address this problem, we have something called median. What is median? Median is the central value, right? Middle value in sorted, we sort the values in ascending order, and the middle value, exact middle value is my median. That's a simple thing. So middle value in sorted data set, even that is a good representative. So we sort everything in ascending order and just take the central value. That's the measure my central tendency. So everything is sorted. Okay. So this is more robust to outliers. Okay. More robust. So that's it. It's pro. More robust to outlier than the mean. Okay. And if you take the whole data set, right? Say for example, the same data set, for example, median of 1, 2, 3, 4, 5. So this will be equal to the middle value. So this will be n plus 1 by 2th value. So this is 5 plus 1 by 2, that is 3. So my median will be 3 here. And if you see that median is the just central value, it will divide the complete data set into exact 2 halves. That's the median, central. 1 half and 2 half. That's median. And if it's n is even, then what do we do? For example, median of 1, 2, 3, 4, 5, 6, then this is n plus 1 by 2th. So that is 7 by 2, that is 3.5th element. What is 3.5th element? In the middle of 3 and 4. So the middle would be here, 3.5. 3.5th element is the 3.5th element here. So this will be average of 3 plus 4 here, because my data is also like that. That is 3 plus 4 by 2. So if you can see here, even this divides the data into 2 parts. So the definition holds, and this is the exact middle. Okay. So this is for odd and even. So the pro, what I mentioned, this is a pro, that it is more robust or not impacted by outliers. Okay. This is pro is not impacted by outliers. This is the problem that we are solving when we have outliers not impacted by outliers. How is it not impacted by outliers or extreme values? Say for example, in the same one, if I have median of 1, 2, 3, 4 and 100. So this will be my n plus 2th value only, right? And this will still be 3. Even if I have 100 here, because everything is sorted in ascending order and I take the middle value. So this doesn't impact. That's that's why it is robust to outliers. Okay, the median. And the cons is, what is the con? We are looking at the middle element. Okay, it does not take into account all the values. It is just taking the middle value. What is just finding one value which is there. It is not taking into account other values. Okay, so that's the con. It is not talking about other values. Okay, as you see here, right, in this, it is taking into consideration all the values. It is summing them up. So the contribution is from all the values in the mean. But in median, no, just one value. What is the center value? I'm just talking about that. I'm not looking at the other values at all, just the central position. Okay, that's a con. Does not use complete information in dataset. Only one value, complete information in dataset. That's the con of this. I hope median is clear. Then the next is simple mode. What is mode? Mode is the frequency, highest frequency. Okay, most frequent value in data set. For example, mode of 1, 2, 2, 2 and 3. What will be the mode? It should be equal to 2 because 2 is there 3 times. Okay, this is the mode, most frequent value. This is simple. Okay, and why are we studying this? Because always the numbers may not be, it's always when we are dealing with data, they may not be numbers only. Sometimes we are dealing with categories. So whenever we are dealing with categorical data, so useful. Okay, useful here for categorical data. For example, when we are discussing about gender, okay, male, female, others, whatever. So whenever you're talking about that, so this mode of the data will give me that the data that I have collected, okay, it has more male or more female. So whatever is more, right, that will be the mode of my data in this category. Or ethnicity, blood group. So I can count which is the most frequent blood group. For example, what is the most common blood group, right? So in case of blood group, so in a sample I can find out what is the representative. For example, in a sample, 7 out of 10 are female. So I can tell that female is the representative here, right? Because 7, that is the most frequent if we have male and female only. Okay. So female will be the mode. So because the mode is 7 and rest 3 are only male. So this will be my mode. So in categorical data, this becomes very important because we cannot measure in any other way. How will you count? Okay. So that will give me. Similarly, blood group. So there are different blood groups are there, right? A, B, AB, O, like that. Both positive, negative, etc. Okay. So from these samples, we can find out what is the, if I take a sample of people and then I ask you like which is the representative blood group. So in such kind of categorical data, okay, there, this is very helpful. Which is the most frequent blood group, that will be the representative or central tendency of that sample. I hope this is clear. What is this? Okay. So this is the pro also. So this is the pro. This is the central tendency. Central tendency used for only, that is used for categorical data which cannot be counted. Okay, which does not have numbers. So categorical data. And this is only and the categorical data is of two types. This is nominal, what I'm talking about. There is ordinal, there is some order in that. So I will discuss about that later. But understand broadly, this is categorical data. Okay. We have certain group of data and we want to find which category or group is most frequent. And that's how we can measure that each group. Okay. So if we measure the frequency of each mode, each frequency of each category, that will give me the mode or the central tendency of that sample. I hope mode is clear in the utility why we are studying. Okay, mean and median doesn't measure that. So mode is useful for this categorical data. Okay, if that is clear, measure of central tendency, if that is clear, then let's move to the next one, that is measure of dispersion. This is important. Or spread. Measure of dispersion. Or spread. So we'll go one by one. With the simplest, first one is range. This is the simplest, most common. As soon as we have a data, we try to find out what is the range. For example, whenever we have a salary, job listing, job posted, right? We try to find what is the range of salary, what is the maximum minimum. That's the first thing we pay attention to. So that's why range is the most simplest and most frequently used. So that's the first thing what is the spread of the data? What is the minimum maximum range? That gives me the spread of the complete data, right? How much is the range? Price range, we talk about that. What is the range of price we are talking about? That's the most commonly used, and that's why it's important. It tells me how, in what spectrum is the complete data distributed. The price is distributed or the salary is distributed. What's the range of that? So this is the simplest measure, simple, and it just range is equal to max minus min. For example, same thing, range of 1, 2, 3, 4, 5. This is 5 minus 1, that is 4. That the range is maximum minus minimum. So this is my range, 5 minus 1, 4. Simplest to do. So this is easy to calculate. That's the pro of this. Okay. And the con is that it is just considering the two extreme values. It is not taking all the data in the distribution into account for measuring this. So only the first and the last, the max and the min, is taken into account. So it is not taking everything into account. That's what is the drawback or the con of this. So it cannot be like the exact representative of this, because it is not talking about all the data points here. That's the con. So range is simple. Next one is variance. Variance is the actual, this measures the actual spread of data. Spread, how spread out the data is, measure spread of, this is the actual spread of data points. So we have the mean. Say for example, if we have a normal or a Gaussian distribution, and we have the mean here. So this, how far a data point is from the mean, the distance. For example, if this is the mean and my data point is here, so there is some distance. Say my data is x here, so there is some distance between the mean and the data point. So we take this distance and square it, so that that difference is amplified. The distance is amplified, the spread is amplified, so that we know how spread it is. So we amplify that, and to measure that how actual on both the sides. So this is, and we square it. So squaring it, what it will do, that I'm just worried about the distance. So if this is like d distance, this is also d distance. So this is like plus t, this is minus t. I don't care whether it is plus t or minus t. I'm just squaring the distance. I just want to find out how far the data is from the mean. I don't care whether you are positive or negative, but you are far away from the mean. So I'll just square it to amplify it, and also to change the sign into positive. So I just discuss about the magnitude. So it solves two problems. First of all, it amplifies the distance. Further, if it is very close, it won't impact much. But as it goes farther and farther, the impact is amplified, and it shows that the data point is very far, and it's easier to measure. For example, if you square it, right, 1, 2, 3, 4, 5, and then 10, like that. So if you see 1 square is 1, but if you see 10 square is 100. Here the difference is only 1 to 10, but here its distance is 10 times that, and this is now 100 times. So due to squaring, the impact of the distance, how far it is from mean, that is amplified. That's what it makes. So the measuring it becomes easy, because it's obvious. This data is far. I hope you get the point. So this is a measure of distance from. So let me write the formula directly. So sigma square. So that's the symbol. Sigma square is the variance. Sigma square. We'll talk about sigma is standard deviation. We'll talk about that next. So this is 1 by n, and then I'll be talking about this is the population. Okay, I'm talking about population variance. I'm using the symbol sigma for population, as I discussed here also, right? Whereas, so this is your population mean and the sample mean. Both are different. Population is mean, sample is x bar. Similarly, population is sigma square and the sample would be s square. Okay. And the formula for this will be 1 by n sigma I equal to 1 to n mu minus xi or xi minus mu, whatever, xi minus mu, whatever works. This is for population. Simply for sample, we write it as s square. This is 1 by n. We take it as small n, capital N for that, for differentiation. I equal to 1 and xi minus x bar square. So this is your sample mean. This is your population mean. There is one more s square. There is a correction factor called Bessel correction. Bessel correction. So instead of n, we use n minus 1. I'll create another video for that, why it is used. So this is an unbiased estimate. This is a biased estimate, and for removing that bias or taking an unbiased estimate, we instead of n, we have n minus 1. There is some math and calculation, some intuition behind that. That is called Bessel correction. I'll discuss about that sometime. I'll write it Bessel correction for unbiased estimate. Instead of n, we have n minus 1 in the denominator. That makes it unbiased. Okay, I hope this is clear, simple. So next one is standard deviation. Standard deviation is simple. We have heard about that. Standard deviation. So variance is the spread. Standard deviation is the square root of. Standard deviation is the square root of variance. So it measures the average distance of the points from the mean. Okay. So distance of each point, average distance. So this is square of the distance, and that measures the distance itself. Standard deviation measures the distance, and this measures the square of the distance. That's the difference. So if I have variance, if I take a square root of that, then I'll get a standard deviation. That's what it is. Standard deviation is. So this is represented by sigma, and that simply it is written as same formula, variance of x. This is your sigma. So for example, let's do it. So sigma is like if you see in the Gaussian also, let me draw the Gaussian here again. This is my Gaussian distribution, and for example, this is mu. So the significance of mu in Gaussian distribution, or the sigma, the standard deviation is, so there is one rule called 68, 95, 99 broadly. So 68% of data is one standard deviation away. This is plus minus 1 sigma. This is plus minus 2 sigma. This is plus minus 3 sigma. Approximately this much of data is there. So if the standard deviation is sigma here, sigma. So if I go here, so 68% of my data will be in this range. One standard deviation plus minus. So this is my mu. I go minus sigma here and plus sigma here. This is sigma plus, this is minus sigma. So 34% here, 34% here on both the sides. This is a normal distribution PDF. So 68% of data will lie here. Similarly, if I go 2 standard deviation till here, then 95% of data will lie here. And if I go 3 standard deviation till here, then 99% data will lie here. So that's the importance, and that's what we use on standard deviation. That's the most common utility, standard deviation in Gaussian. And normal distribution, they are very common. It measures the distance of each data point from the. So for example, if this is mu, and this is the x point, right? So it measures the distance t from here. How do we do? Let me write the formula. So this is, say for example, I'll give you a standard deviation of 1, 2, 3, 4, 5. This is a sample, right? So what is my x bar? This will be equal to 3. This is my mean. No problem about that. So what will be my standard deviation? This will be equal to square root of distance is always square root of the values. So 3 minus 1 square plus 3 minus 2 square plus 3 minus 3. For each I am taking the distance, what is the difference, and squaring it, and then I'll take square root of all. And then there's 4, and 4 minus 3 or 3 minus 4, square it, doesn't matter, plus 5 minus 3, squaring, and then average distance of all the data points will give me standard deviation divided by 5. This will be equal to 3 minus 1 is 1 plus 4 plus 0 plus 1 plus 4 by 5. 4, 5, 10. So square root of 10 by 5, that is square root of 2. That is 1.4 approximately. Approximately 1.414. This is my standard deviation of this data. Our standard deviation is clear. We have discussed about this a lot. There's one more measure of distribution, data distribution, which is simpler than this. So the units of variance, if you see, that is square, distance square. So whatever is the unit here in variance, that will be square of the distance, square times. Okay, and this is a square root, so the units will become same. Units will become same, whatever the distance. For example, if I'm measuring height in centimeters, so my standard deviation will be in centimeter, but my variance will be in centimeter square. Okay. Another one, next one is mean average, mean absolute. So I want to calculate the distance, right? Mean absolute deviation. Mean absolute deviation. So simple. This is average absolute deviation. Instead of square, it is absolute value. So square will anyway make it positive. Absolute value also makes anything positive, right? Absolute value of x is x. If it is positive x, then it will make it x. If it is negative, also then it will give me x only. It just captures the magnitude, not the sign. Okay, so this is average absolute deviation or distance deviation from mean. Okay, this is less sensitive to extreme outliers. So this is less sensitive to extreme outliers. Say for example, instead of 5, if I have 100 here, right, this 100 will be squared, and this will make the standard deviation move towards the outlier. But if I am not squaring it, the impact is not so much amplified when I use absolute value. So that's the pro of this with respect to standard deviation, mean absolute deviation, that it is less or more robust to outliers. More robust to outliers than standard deviation, because standard deviation uses squared values, which amplifies the difference. Okay, what is the formula for, and in short we write it MAD, mean mad. This is equal to 1 by n sigma I equal to 1 to 1, same thing, and xi minus x bar. This is the sample mean, and this is the absolute value. So this is average 1 by n, and this is the sum of all absolute value differences. Say for example, same thing if I calculate mad for that. For example, mad of 1, 2, 3, 4, 5. This will be equal to, so mean is 3. So this will be 3 mod of 3 minus 1 plus mod of 3 minus 2 plus mod of 3 minus 3 plus mod of 3 minus 4 plus mod of 3 minus 5 by absolute by average 5. So this is not squaring. So 3 minus 1 is 2 plus 1 plus 0 plus 1 plus 2 by 5. So this is equal to 6 by 5. That is 1.2. So this is less than standard deviation. So another way, when we have outliers, when you think that there are outliers and its impact should not be amplified, then we consider mean absolute deviation. I hope that's clear. So next one, this is important, skewness. I have discussed this earlier also when I was discussing moments. I'll put the link of that video, but I'll discuss it again in detail here, skewness. So this is the third moment. So when we talk about moments, right, moments of a distribution, this is the third moment, third normal moment. Variance is the second moment, and then we'll discuss about kurtosis, which is the fourth moment. Okay, so this is the measure of asymmetry of data distribution. This is measure of asymmetry of data distribution. For example, if it is a normal distribution, this is bell shaped and the data is symmetric. Half of the data is here, half of the data is here. So around the mean, means half of there, half other side. Okay. And the variance, what variance or standard deviation captured, that whether the data is close to mean or spread out, it is far from mean. That's what the distance measures. But here, if the data is asymmetric or not, none of the metrics measure that. And if I want to measure what if my data is asymmetric towards any of the directions, then skewness measures that. For example, if my data is right skewed or left skewed, okay, it can be like same thing. I have like this, I have like this. So my data can be like this, okay, or it can be like this. You see, this is like right skewed and this is like left skewed. If it is right skewed, it is called positive skew, and if it is left skewed, it is called negative skew. So most of the things here, if you my go-to place is Wikipedia. So let me show you Wikipedia, just a minute. So skewness. So if you see, I'll take the diagrams from here and then I'll show you. It's very good. Refer Wikipedia, I mentioned earlier also. Here it shows, right, negative skew, positive skew. Right, there's one more good diagram here at the bottom somewhere I saw. Where is it? This one. This is a very good diagram. Let me take a screenshot of this and explain you. So I'll put it in the notes. Okay, and let's come back to the notes. So if you see at this skewness tells me the asymmetricity, how asymmetric my data is. This is the positive skew, which is this is skewed towards right side. This is the positive skew, and this is the left side skewed or negative skew. Okay, and this is symmetrical. This is kind of normal distribution. It is not skewed, no skew in this data. And if you see, due to skewness, what happens is the median, okay, mode and mean. Here if you see the relative position, so I'll write it here. Just write it, then you will observe what am I saying. So mode is less than, okay, it's on the left side, and median, then the mean. And here if you see, the mean is less than, the median is less than the mode. Why? See, the mode, as I mentioned earlier, mode is the of the peak. That's the most frequent element, and there in the PDF will be the tallest. That's the most frequent. Around this number I have seen the most number of times, and so the probability of that number is the highest, and that's where we have the peak. So if you see, the peak is on the positive side skewed, the peak is on the left. So my mode is on the left, that's the least value. And here if you see the mode is, if it is negative skewed, the peak will be on the right side and there will be a long tail towards the left. So here if you see, that mode will become the highest, and similarly mean and median. Okay, yeah, mean and median. And since the data is like tail has become long here, it will pull the mean towards itself. Because a lot of data, the tail is long, so the data, it will pull the mean, instead of the peak, it will pull it towards here, this side, other side, wherever the tail is long. So the mean will be pulled towards the tail, so the mean will go that side. Similarly, since the data is skewed this side, the mean will be pulled this side. And median is the central data, it will always remain in the middle. It's not impacted by, because it doesn't take all the data points into consideration. So the median stays as it is, but this mean and mode will shift. I hope that is clear, depending upon the skewness. That's why understanding skewness or the third moment is important. Okay, let me write it down, whatever I mentioned now. So you saw positive skew. So what is on the positive skew? This side you see the tail is longer. The tail is longer on the right. Okay, and bulk of the data is here. This is the bulk, but the tail is longer on the right, and just the opposite on this side. That's what I mentioned. And the zero is perfectly skewed. Okay, for example, if you see salary of employees in a company, right? So mostly, if you see, most of the employees earn less salary, but some higher executives, higher executives, VP, CTO, CEO, CFO, they will earn a lot of salary. So they will pull the mean towards the higher side. But that's not the actual case. Most of the people are earning a modest salary, that they are here. But just few people who are earning on the tail side, like this side, there will be few people here on the tail. This will not touch there. There are few people who will be earning a lot of money. If this is the mean, right, this will be somewhere mean median, right? This is like say an average. So this is like 20 lakh is the CTC average. So some people will be earning in like 2 crores, 5 crores, like that. And this will pull the mean towards right. But that's not the actual representative, because these outliers, this skewness has pulled the mean higher. So in all these cases, if you see, even companies report their median salary, or in the placements also, that median salary is reported, because mean may not be a good representative because of this reason, because the data may be skewed towards one side. I hope that is clear. Why skewness measure is clear, and if I have a measure of skewness, then I will know a lot of information from the data itself. Nobody can then lie to me by saying that average package is this average. Don't tell me the average. Some people might have got very high package. Tell me the median or the mode if there are bulk companies hiring in bulk. So most of the people will have the same salary. I hope you get the point. Next one, kurtosis, very important. Kurtosis. The names may seem a bit odd, but the concept, if you understand, this is the fourth moment. First moment is mean, second is variance, third is skewness, and fourth is kurtosis. Kurtosis, it measures the tailedness. This is measuring asymmetric, whether data is symmetric or this is symmetric. This is asymmetric, on which side it is asymmetric. This fourth moment measures the tailedness, how fat or thin the tail is. Okay, measures the tailedness of data distribution. How much, so it describes how much data is there in the tail versus the rest of the peak. Okay, it's there. Okay, it's so, and if I have a long tail, what do I mean? As I mentioned, I have talked about it. If I have a long, fat, thick tail here, right, this means that this is the mean here, somewhere here, mean here, and I have a long, fat, thick tail. So this means that lot of data is there on the extreme side. Means I have lot of outliers. So this kurtosis will tell me that the magnitude of outliers present in my data. Whether I have, if it is a thick tail, then outliers are very much. If it's a thin tail, then the outliers are not so much. That is extreme values. If the tail is thin, means values far from the mean. Those are extreme, right? Values close to the mean are close to mean. That's the central tendency. So everything, if everything is near, no problem. But if they are far from the mean, then those are outliers. They don't happen. That are not normal. They are rare, exceptional. These are outliers. These are extreme values. And this kurtosis measures that. What is the measure of that outlierness or exceptional values are there or not? So just looking at the kurtosis of the data, we can make out whether we have outliers, and if yes, then what is the how much value they are bringing in there. So let's understand it from the Wikipedia itself. So kurtosis. So I wanted just read through this. This is a lot of information, but I look at it for the graph. So I'll show you this graph. Just copy it. And then just have a look at this graph. So these are the distributions for many types. As I mentioned, right, there are a lot of distributions. You can't even remember. So we just talk about few which are common, but there are many types of distributions. Just for this data, right? If you see, so here, just read it here. So there are some values here you saw. I'll just look at here. U, W, N, L, S, D. These are names are there, right? Just look at it. What do they mean? D is for Laplace distribution here. S is for hyperbolic secant distribution. L is for logistic distribution. N is normal. C is raised cosine distribution. This is Wigner semicircle, and U is uniform distribution. So there are so many distributions whose kurtosis is drawn here together. And let's come back to the sheet and see. So if you see here, some for this N, right? N is normal, which is color black. So this is the black one. This is a normal distribution. Normal peak, normal tail. This is the normal. Everything is measured against normal. So this is my reference. This black one is my normal. 0. This kurtosis for this is taken as 0. And this is a reference for all. So all these kurtosis is measured with respect to normal. So this is 0, and everything like Laplace is the green one. So if you see, Laplace is green. S is 2. S was secant something. Okay, that is the orange one. And then 3. D was Laplace. S was secant. D was what was D? D was Laplace. L was logistic. L is logistic. D was Laplace. You see, Laplace is so peaked. Okay, and also you see the tails here. So just go through this, and this is very good representation how peaked, if the data is peaked or there. And if you see there's uniform distribution also. There's no tail at all. Everything is in the center. Everything in the center. So no tail, no outliers. Everything. This is a square box. Everything is in the purple box. So this is the. So U is uniform. That has that negative kurtosis. Okay. No tailness. 0. Okay. But everything is measured with respect to normal. So let's come back and understand. So it measures the tailness of data. Okay. And then there was a more thing. So let's see. There are 3 kinds of kurtosis. There's one more diagram probably I saw here. Not here, maybe somewhere else. Let's come back. I'll show you. So there are 3 types of kurtosis. Okay. I'll just take it from other place. I'll just bring the data. Okay, so there are 3, right? So before going through this, let me tell you what am I telling. So you saw there are so many types of, so depending upon these all are having different kurtoses, and these all kurtoses are categorized into 3 broad categories, and normal is the base. Normal is 0 kurtosis, right? And that's what we measure as excess kurtosis. Excess, okay, extra. So excess kurtosis means kurtosis greater than normal. So my normal is considered as my reference, and normal distribution, and this is normal distribution or Gaussian distribution has Normal distribution has kurtosis of 3. Kurtosis equal to 3. And excess is anything above 3. Anything above 3. So this is taken as, this has excess kurtosis of, what will be the excess kurtosis of normal? Excess kurtosis of normal or Gaussian will be 0, because this is the reference. So this has basic kurtosis of 3. Anything more than 3 is counted as excess kurtosis. So excess kurtosis for normal distribution is 0, and that's what is shown in this graph, that this is 0. This is what 0 means. Everything, because normal is what is we take as reference, and everything we measure against that. That is the most studied distribution. So excess kurtosis for normal is 0, and everything is measured against that. So mesokurtic is excess kurtosis 0. So this is your normal. This is called mesokurtic. This is your normal. Okay. This is normal, and this is your excess kurtosis is. So normal, and I'll write excess kurtosis equal to 0. That is EK. That is for normal, excess kurtosis is 0. So this will be your mesokurtic. The names are a bit odd, but just understand the concept that this is a normal distribution, and for a normal, excess kurtosis is 0, but its own kurtosis is 3, and that is taken as reference. That's why I make 3 as 0 now. Okay, and kurtosis formula generally, that's a fourth moment, so it has expectation of 4th degree. Okay, so you take expectation of the some xi minus xi minus mu to the power 4, the expected value of this. This will be your kurtosis. You can see that in the Wikipedia also, somewhere it will be, yeah, kurtosis of x is x minus mu by sigma to the power 4, like that. Okay, so that is to the power 4. That's the fourth moment. So this is your mesokurtic. Normal. So tails are neither too thin or not thick. That is my reference. So these are neither too thin or not thick. That is my normal. Okay. So not too thin, not too thick. Leptokurtic is the next. This is high kurtosis. The lepto is high kurtosis. High kurtosis means excess kurtosis is greater than 0. EK is greater than 0. Okay. And here if you see, the tails are, this is your normal. If you see here, this tail is fatter. Here, so if you see, the tail is fatter than the normal one for the blue line. This is your leptokurtic. So kurtosis is high. So the tail is thicker, and even the peak is higher than the normal. So more of the okay, high concentration of data around the mean, and also on the tails. So lot of data around the mean, and lot of data around the tails also, lot of outliers also, thick tails. So that is leptokurtic, high kurtosis. Okay. So high, for example, these are like Laplace distribution. If you see Laplace, right? Say this Laplace, this thing D was Laplace. So it has a very peak. So the peak is very high. So a lot of data is around mean, and the tail is also thick. If you see the red one, the tail is also here. The thick tail is here. The tail is thick. That's what we mean. So that is lepto, high kurtosis. And similarly, the opposite would be, for platykurtic would be excess kurtosis is high, kurtosis is low kurtosis, and here excess kurtosis is less than 0, negative. For example, if you see that this is nothing, even the peak is small, and in the tails are also thinner than normal distribution. Okay, so almost like kind of, if you see here, uniform distribution, it has negative kurtosis. So most of the data is uniformly distributed, nothing around the mean. It is not concentrated here. It was like in this Laplace, if you see, it is concentrated on the peak, or it is in the tails. Here everything is uniform. Most of everything is uniform. Nothing around the tails. Everything is uniform there. So kurtosis is negative. No peakness, no tailedness. Here it is very high peak and very high tails. That's what kurtosis will tell you, how my data is distributed. So this will tell me the spread of the data. I hope kurtosis is clear. It tells me the degree of mostly the tailedness, and if the tail is varying, then the peak will also vary along with it. Okay. So this is your measure of spread of the data, so that I understand what's the measure. We saw measure of central tendency, then we saw how the data is distributed, or dispersion, or the spread, all the measures of that. And now let's move to the position, respective relative position of data within the complete data set. So that is your measures of position. This we know already. I'll just formalize the understanding. We all give tests and we know the first. Okay, so this is helps us understand the position of specific value in the data set. Okay, helps us understand relative position of data of a specific data point, in the data set. So that's what it measures. And there are ways to measure this: percentile, quartile, and then we'll talk about one of the range metric also. So let's see percentile first, most common one, percentile. We give exams and all the scores that we get, like JE, etc. nowadays, GMAT, wherever you go, you will get percentile. What is a percentile? So percentile is nothing but, what do? We get percentile out of 100%. That's the name is coming. So percent, this cent word is coming from 100, per 100. So per 100, what is there? So percent means we divide the data into 100 equal parts. Okay, this is a way to divide data in 100 equal parts. Okay, and then whatever is the percentile, say for example, out of 80 people, if my percentile is, say for example, I have got 80th percentile in any test, that means that at least, okay, at least 80% of the people scored less than me, or in other words, my score is higher than at least 80% of the people. Okay, my score is higher than 80% of all other people who took the test. Of all other people who took the test, who took the same test. That's what 80 percentile means. Okay, you divide the complete, if there are 1000, we divide it into 100 parts, and then out of, if your score is, say for example, out of 100, if you scored like 67, and still your percentile can be like 80th, because the number of people who scored 67 or more is only 20%, and 67 or less is 80%, because you divide the complete scoring into 100 and number of people who, percent of people, not the number, the whatever be the count, 80% of the people scored less than you and 20% of the people scored more than you, and you are on the 80th percentile. That's what it means. Simply, if I write it formally, like kth percentile, kth percentile, say percentile k is equal to at least, what do we say, at least k percent of data values are less than or equal to it, less than equal to given value, equal to it. Okay, let it be. Percentile, everybody, we use it, and now I think it's formalized and it's clear. Okay, so that's your percentile. Now let's move to the next one, that is quartile. Quartile is again the word itself. Quartile. Quartile is coming from quarters. We divide the data into 4 parts. Percentile was 100 parts, quartile is 4 parts now. We divide the complete data into 4 parts. The relative position was with respect to 100 parts. Here I divide the data into 100 parts and put myself there, or whatever the score I have, and then I see out of 100 parts, where do I stand? In which part I am? Out of 100 parts, I am on the 80th part. 80% people are below me and 20% are above me in a test. Similarly, quartiles are divide the data into 4 parts, and I lie in which part. Okay, so that's the idea of quartiles. So these are against percentiles only, special percentiles. So that was 100 parts. And now if you divide the complete thing into 4 parts, then each quarter would be 25, 25, 25, 25. So that is like 25 percentile, then 25 to 50 percentile, 50 to 75, and 25 to 100. So these are the 4 parts, and these are the 4 quarters, okay, or quartiles. I hope that is clear. So special, these are special percentiles. Special percentiles that divide data into data set. Data, when I mean the complete data set, all n data points. Data set into 4 parts. Okay. And this is again not affected by outliers. Not affected by outliers. Okay, simply this is relative comparison. So again, everything, this is whatever the position is again relative with respect to the data set. That's for the whole idea. So what are the 3 quartiles? So we write it as Q1, Q2, and Q3. These are the 3 quartiles that we measure. So this is like 0 to 25 percentile. This is percent means percentile. Write it percentile itself so that you don't confuse. Then it is above, okay, up to below which, okay. So Q2 is up to till 50th percentile. So I'll write up to 25th percentile, then up to 50th percentile, and then this is up to 75th percentile. Okay. And 50th percentile means the position is 50th, that is in the middle. So generally the Q2 end is, this is the median. So median is the measure of the percentile also. So the 50th percentile is the median. Okay. So for example, let's understand. And how do we calculate it? So this will be, let me write it. This will be this will be equal to Q1 is n plus 1 as it is into 1 by 4 equal to n plus 1 into 2 by 4, that is half, is equal to n plus 1 into 3 by 4, that is quarter, 75 percentile. So these are the 3 quartiles, Q1, Q2, Q3. So data less than 20%, 25th percentile, less than 50th percentile, and less than 75th percentile. Let's understand quickly with an example. So we have one data, let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and let's have an outlier 100, so that I'll show you it doesn't, outliers don't impact because it's relative position. I'm not taking into account these numbers. I'm not summing or adding it up or multiplying anything, so it won't impact. So that's the whole point. So I'm not doing any mathematical operation or including it in my calculation. I'm just taking the position, then it won't impact, and that's how I'm outlier proof. So what will be my first quartile? Q1 will be equal to, how many data points are there? 10 plus 1, 11. So this will be n plus 1 will be 11 plus 1 into 1 by 4. That is 12 by 4. That is equal to 3. So this will be my, this is my Q1. Q2 will be 12 by 2. This will be 6. So this is your Q2. Similarly, Q3 will be equal to 12 into 3 by 4. This will be equal to 9. So this is your Q3. So these are my 3 quartiles. So if you see, even if you have 100 or 1000, it's not impacting where my Q1, Q2, Q3 will be. And now what are the 4 parts? If you see, this is dividing into 4 parts. This is my first part. This is my second. Let me do a different color. This is my second part. This is my third part. If you see, this is my fourth part. First part, second part. So quartiles are 3, but the parts, they are 4. Q1 is till 25th percentile, Q2 is till 50th percentile, Q3 is till 75th percentile, and then beyond that is till the 100th percentile. So these are the 4 parts which it is dividing, and these are the metrics Q1, Q2, Q3. This is how we measure it. Very important. Okay. And then quartiles are the, so we have, when we will see, and again when some plots when we do. Okay, so there is something called box plot. So it is like this. I'll just draw it in a rough way. So it looks something like this. Let me see. This is there, and there will be some big box like this. You will see some plots like this. Okay, and there will be like this, and like this, and then like this. This is your box plot. Okay, so let me write all. This is the minimum value. This is the minimum value, starting point. Okay, and this is your Q1, this is your Q2, this is your Q3, and this is your max value. Okay, Q2 is also your median. So this will also tell you where your median lies. So again, if you see here, it is dividing the complete data into 4 parts. This is your first part. Okay, and then the second part, and then the third part, and then the fourth part. So that's what your box plot gives me. First, second part, third part, fourth part. I hope now quartiles are clear. And then next is my IQR. So that's a measure of a range or dispersion of data, spread of the data. So IQR is interquartile range. IQR. This is used for, this is the most common method to identify outliers. Okay. So this is again a single number, gives me this single number that gives the measure of middle 50%, the spread of, measure of spread, or I'll just write spread of middle 50% of the data with respect to the percentile, 50% of data. Okay. And this is a more robust measure of spread than range, because range is impacted by outliers. I'm just taking the middle 50%, this bigger box. This is the middle 50%. This is first 25%. This is the last 25%. So this, the data in the box, this is your IQR. So this will give me the middle 50% of data where it is lying. So it is not impacted by the minimum or maximum value. So that's why it is more robust than range. More robust to outliers than simple range, because range is just max minus min, right? Say for example, this will be like the middle 50% means this range. What will be this? Starts from here and here. So this will be like Q3 minus Q1. This is your middle 50% of the data. This is first 25%, last 25%, and this is your IQR. So your IQR is equal to wherever your Q3 lies minus Q1. So here in this data, whatever we had, where is my Q3? Q3 is at 9 and Q1 is at 3. So what will be my IQR? Here itself. If I want to calculate IQR also, so my IQR will be Q3 minus Q1. This is here equal to 9 minus 6, 9 minus 3. That is equal to 6. This is your IQR. Simple. Very simple. Okay. And this IQR is used for outlier detection. How? So this is used for outlier detection. This is the most common tool when I'm doing exploratory data analysis, right? So I use IQRs for one of the methods to see after the plot, etc. Right? This is also one of the measures to understand the what are the data points that may be potential outliers. It gives me that information. So how? So again, I'll write it for you. IQR is a standard tool during EDA tool for outlier detection. So So we define some fences, some boundary, and any data that falls outside the boundary is a potential outlier. Okay. So based on the IQR, I decide some more extra. I'll give some padding, and I'll decide these are the boundaries. This is my middle 50th percentile, and I'll give some boundaries, extra padding on both the ends, and anything that falls beyond that, that will be a potential outlier. I'll flag them as outliers and leave it for the expert to review whether it's an outlier or not. So let's see. So values that fall outside the boundaries, outside the fences or boundaries, the fences that I decide, guarding boundaries, are called potential outliers. Okay, for example, so I'll define, how do we define the lower and upper fences? So lower fence is equal to, so this will be Q1 minus 1.5 into IQR, and the upper fence, the upper boundary, is equal to Q3 plus, so anything, again same thing, 1.5 into IQR. So this is your, I'll take the same example. Let's copy it. And let's see what are the outliers in this data. So it can, whether it can flag potential outliers or not. So what will be my lower and upper fence? So my IQR was equal to 9 minus 3, that is equal to 6. So what will be my lower fence? Is equal to 3 minus, so my Q1 is 3, Q1 minus 1.5 IQR is equal to 3 minus 1.5 into 3, right? 1.5 into IQR, right? IQR is 6. So this will be 3 minus 9, that is equal to minus 6. That's my lower boundary. Now what is my upper fence? This is equal to Q3 plus 1.5 IQR. Equal to 9 plus 1.5 into 6. This is equal to 18. So this is my upper fence. Anything beyond this, greater than this, is an outlier. So if I look at my upper fence, lower fence minus 6, so any values less than minus 6? No. But if I look at the upper fence 18, and so I will see that in my data there is 100. So I can mark this value, I can flag this value as an outlier for the expert to review, check whether this is an outlier or not. And they can decide whether this is an outlier. The subject matter expert will understand. Okay. I hope this is clear, what is IQR and how it is used for outlier detection. So all these techniques that we discussed today, this is kind of revision. You might know this already, and these are used during the exploratory data analysis, when we just get the data, and first step is to see what is the data about, what is the distribution like, without having the actual PMF or PDF of it. Just from the data itself, what analysis can I do? And this is what we do. Okay, this is what we do. So let's do a quick revision. We try to find the measure of central tendency. What is the mean? What is the median? What is the mode? Mean is not outlier proof. Median is outlier proof. Mode is for the categorical data, because their mean and median won't make sense. This is the thing to look for. Then measure of dispersion, or the spread of data. Then we talk about range. That is the simplest thing. What is the range of data that I'm looking at? Variance of the data, how spread out the data is. Variance and standard deviation kind of measure. This is just a square of standard deviation. So we'll measure, this is the second moment also, we'll measure how the data, whether it's very spread, means it is very close to the mean, or it is spread out far from the mean. If the variance is small, means the data is lying very close to the mean. And if the variance is high, means the data is spread out far from the mean. That's what it means. Mean absolute deviation is just, it takes the absolute value and it takes the distance from that, from the mean, and that's what it gives. It's more robust to outliers because it is not squaring the value like standard deviation. So this is also used. Okay. Then skewness, this is the measure of asymmetry, whether my data is asymmetric or not. It is whether it's left skewed or right skewed, we saw here. And because of the skewness, how mean, median, mode, they get impacted. Mode is the peak of the data, and how the mean and median, okay, mean will be pulled because of outliers towards the right here and towards the left here. And that's when we saw that mode and median. Median will remain the same because it's not impacted, it doesn't take other data points into account. And then we saw kurtosis, which measures the tailedness of the data, okay, how tailed my data is. And we saw three kinds of kurtosis: mesokurtic, platykurtic, and leptokurtic. In that, we also saw excess kurtosis. We take normal distribution as my base, and everything is measured because normal is taken as a reference and everything is measured against normal. So kurtosis for normal is 3, but we take it as a base, and we tell that excess kurtosis of normal distribution is 0, and other distributions are kurtosis for other distribution is measured with respect to this excess kurtosis. How good or bad or how tailed or peaked it is with respect to the normal distribution, which we know very well. Okay, so normal is extra kurtosis is 0. High kurtosis means the kurtosis is greater than 0. Positive, which we saw here, like this is D is a Laplace distribution, which is so peaked and the tail is also big. And then low kurtosis is for the uniform distribution, which is very no tail at all, and everything is not peaked also. Everything is like uniformly distributed. So nothing is like it is data is just gathered at few points. It is spread out evenly. So that's what it means, leptokurtic and platykurtic. So after seeing this kurtosis, then we saw the measures of position. So after that, we have seen the data, how they spread the data is. We see that measures of position. What is the relative position of the data within the data? What is the relative position of each? So we saw percentile, that is with respect to, we divide the data into 100 parts and see where my data point is at which point. Say for example, if my score in a test is 80th percentile, I have got 67 marks, means I have scored better than 80% of the people, and 20% of people have scored better than me. That's what it means. Then there's quartile. This is just a special of percentiles, that now at quarter is like 4. So I divide the complete 100 parts into 4 25 unit parts or 25 percentile parts. Okay. And then Q1 is 25th percentile, Q2 is 50th, and Q3 is 75th percentile. And then we divide this into 4 parts based on the quartiles. And then we saw about interquartile range, which measures the range. It's a measure of the range or spread of the value. It measures the middle 50%, that is Q1 to Q3. And we also saw that it's the base for this. Quartiles are the basis of the interquartile range, and then this quartiles are the basis of box plot. And then we saw the use of box plot. This is used for viewing the data. And then we saw how IQR is used for outlier detection, where we decide the upper and lower boundaries or fences, that anything which is less than Q1 minus 1.5 IQR, anything which is greater than Q3 plus 1.5 IQR, we flag them as potential outliers, and then the subject matter expert reviews that and whether it's a real outlier or not. So that's taken decision. Okay, so that's all. These all topics will be very helpful in this. Okay, let me give you one more thing. Once I have understood all these things, still we should plot the data and see, because of very important, one very fun thing, there is something called Anscombe's quartet. Okay, where there was a mathematician or statistician who showed that there were 4 data sets which had all these basic descriptive statistics, which have almost similar descriptive statistics, mean or deviation, everything is like same. But when you plot the data and see, it will be in totally, the shapes of that plots will be totally different. Let me show you what I mean. Let me show you what I'm saying. Anscombe's quartet, this one. Yeah, this one. So if you see this, all 4 have identical statistical parameters. If you read this here, identical statistical parameters, but the graph show that they're considerably different. So these all data points have the same mean, same median, same mean, same standard deviation, variance, etc. But if you see the plot, they are totally, if you see, this is like spread across the center line. This is like a curve. This is just one big outlier, and here everything is like vertical only. Only one point is the data line. So important thing is, even after studying this, whatever we have studied, all these data points, all these ways to understand the data, still after doing all this, we still plot the data and see how does the data look like on the plot. That's very important. Okay, on that note, let's end it. Thanks for watching this video. Have a great day ahead, and bye for now.